So the first thing that I want to do is I just want to go through all of the steps of this synthesis and try to just point out the transformations that are happening step by step, and then I can go to the specific questions that are asked in the beginning of the problem set. So if we think about the original step, so going from here with this reactant and this reactant going to this product, hopefully you can see that the reaction going on here is a Diels-Alder reaction. To get to this product. And hopefully you will remember that the stereochemistry of the resultant product from that Diels-Alder reaction is going to give you both of these substituents on the same side. So both of these substituents, so it would come from this hydrogen, this methyl group, are cis. So the question is, what's going on here is you're just treating this first with a base and then with an acid. So if you're just treating this with a base, I think the most important thing to do is to try and realize what is the most acidic hydrogen in this molecule. So if we look at this molecule and look at the most acidic hydrogens, we would want to look alpha to carbonyl. So you'd have this hydrogen, this hydrogen. Those are the only two that are going to be acidic. The vinyl hydrogen will be somewhat acidic. You could stabilize this through resonance through this carbonyl. The issue with that is that you'd have a double bond, which I've said in class before, but is an alene system. Alenes are not possible within a 6-membered ring. So then this is the most acidic hydrogen, and then the HCl step is so you remove this hydrogen, generate an enolate, and then all you do is quench that enolate. And so the question is, why does it go from here to here? Then the answer to that would be that for some reason this is the thermodynamically most stable product. So it's the thermodynamic product. So going from 5 to 6 is actually a complex reaction, so I'm not gonna, this would be a good one to understand a detailed mechanism for, but really what you have here is you have two things that are going on. You are removing this methyl group under acidic conditions, and you are also eliminating this hydroxyl group. So this is a deprotection, and then this is an elimination. So then we go to this step, and so we look at the reactant and the product. You can say, what is different about the reactant to the product? So the first step is acetic anhydride and zinc. You generate the acetate. Then this is actually a very specialized step that I would not expect people to know, but I think that what you can take from this is that it's very reasonable to understand what are the bonds being broken, what are the bonds being formed. So zinc is a very unique reductant, and the bond that is being cleaved is this bond, and you're left with the hydrogen there. Alright, so then the next step is going from compound 7, so I'm about to hit the 5-minute mark on my videos, so going from compound 7 to compound 8, and I think that again what the most important thing to realize here is that this is a nucleophilic acyl substitution with this molecule right here. So the first step is that you generate an enolate at this position, attacks here, kicks that off. Right. And then so then you would have basically a carbonyl. So imagine this as imagine this as a single bond like that. And so then the way that this is being drawn right now is just it's the enol form of that molecule. And so why is it drawn as it is in the problem set? The enol form is more stable because you can take conjugation throughout this entire pi system.